Okay, okay. So this is a class about partial differential equations. Can you see that? This is a class about partial differential equations. So, well, first of all, what are they? What do they describe? Differential equations are the language of nature, so we can measure rates of change. But we want to make conclusions about things that are not rates of change. Like, for instance, you can measure the speed in your car just by checking rotation of the wheel. But if you want to measure the distance that you've traveled, then you need to do an integral to get the area under the velocity curve. So you pass from the differential equation, the rate of change that you measure, to more useful information. So early examples, or what are they? So certainly every ordinary differential equation is also a partial differential equation. Your ordinary differential equation is going to have like one variable only, and oftentimes in engineering that variable is time. So for example, what are ODEs that you see in your ODE class? We usually see logistic equation. We often see the mass spring system. I'll remind you of mass spring system. It looks something like this. I'll try to talk and then write. So this is like, for instance, a mass spring system equation where you have like a mass on the spring of mass m. Gamma is related to the coefficient of friction. Because of Newton's second law, the mass gets a term with acceleration. Friction goes against the first derivative, and then k is your spring constant. And then capital F represents an external force that's put onto the spring. Of course, I will not give you a detailed explanation of this, from ODE class, but that's like a classic example you might study. And in that class, you learn that the solutions, at least the homogeneous equation, are completely determined by the algebraic character of the equation, namely the discriminant of polynomial m y squared plus gamma y plus k, right? And depending on that discriminant, you can actually completely characterize the solutions, whether it's damped, overdamped, whatever. And for simple forcing functions like sine, cosine, e x, x, or x squared, you have these methods like undetermined coefficients, variation parameters that you go through in that class. So PDE is much more broad. PDE deals with equations that now have both time and space variables. So that makes things immeasurably more complex than ODEs. And it leads to sort of a vast, rich theory that we can only hope to touch on just a little bit. So wade not so deep into the pool, but we'll certainly see a lot of interesting things and a lot of intricate things. Your first ODE that you see actually comes from calculus. So maybe you've seen this equation. Y prime equals f. And you might supplement it with an initial condition, like y of a equals 0. Does anybody want to recall what the solution to this differential equation is? There's a theorem from calculus that is very fundamental. That can do it. But basically, fundamental theorem of calculus says that y should be the integral from a to x of your function f. So, and this is the unique solution. So in some sense, your entire Calculus 1 class is teaching you how to solve that basic PDE. And it's also a regularity theorem because you can start with continuous function f, and the solution y will now be differentiable, not just contiguous. So you start with a continuous function, and then your solution has an extra degree of differentiability by virtue of being a solution to the equation. Those are things that we care about, that do equations give us, like differentiability or other properties. Okay, let me give you an example of something that you might see, that you will see. So here's an example of a PDE. I'll describe the problem and then afterwards write down the equation. So here we go. Let's consider, just for argument's sake, the model of a rigid rod, perhaps of varying density, maybe made out of some kind of metal. And I'll give a function u of two variables x and t. X tells you your position on the rod, and t tells you, how much time has elapsed since an initial state. uxt is going to be equal to the temperature of point x on the rod at time t. So here's what the picture looks like. So you've got some function describing the temperature of the rod. And so this rod is going to have an initial temperature, and I'll set up some boundary condition. And so my boundary condition is going to be, I'm going to keep this side at fixed temperature 100 degrees Celsius. I'll keep this side at fixed temperature 0 degrees Celsius. And I'll write that as follows. And one more condition, let's just say initially the rod was freezing. Yeah, so it's totally fine. So for t bigger than 0, I'm holding the ends at that condition. And for t equal to 0, its initial state is just 0 degree rod. You pull it out of the freezer and immediately heat one end to 100 degrees and cool the other one to 0 degrees. And describing such a situation, that's called the heat equation. So you might get an idea that as you let time go by, you'll warm up to a certain temperature, and this will stay 0. And I guess as time goes by, you might expect to reach a steady state, right? You wouldn't expect the temperature to oscillate forever, being that you're holding it like at a constant temperature. In fact, I challenge you to draw the graph of the temperature like in the final state, namely, if you take the rod and put it down here, from initial point to terminal point, you imagine heating this side to 100 degrees, cooling that side to 0 degrees, holding that for 6 hours, 10 hours. What's the final state look like? Does anyone want to take a guess just based on your physical intuition?
The rod uniform density?
Not necessarily, but if you like, sure.
I don't know, something that looks like 1 over,
We'll keep it uniform density.
like 1 over x-ish. Maybe just take 1.
So I'm hearing something that could be like that. Although it can't actually be 1 over x, right? Because
Right, it is 0.
you need that to be 0.
Could it just be linear?
Yeah.
It's reasonable because a linear interpolation from one to the other. Let us write v of x equal to the limit as t. Limit is as t goes to infinity of u xt, and v of x is called
No.
v of x is called a steady state. And so this graph, I'm basically asking you what is the steady state solution, if there is one. Without actually telling you how the physicists derive this, just at this second, maybe we'll talk about that later. Let me show you the equation that models this behavior, at least sort of like the simplest equation that models this behavior. You want to look at, I'll write it down and then make some comments. So this is a partial derivative of u with respect to t. U has 2 variables. This is second partial derivative of u with respect to x. So that's standard notation that you'll see throughout the text. This k is a constant of proportionality. So this is called the heat equation, also called diffusion. It's called diffusion because it describes chemical processes that diffuse, but heat also obeys such a process because if you look at the way heat disperses, it happens by exciting some molecules that then bump into other ones that get like a little bit less excited, but then keep bumping in, and then the heat radiates outward. So the heat disperses or diffuses in the same way that a chemical will diffuse or disperse in a medium. And therefore, it's described by the same equation, and that explains why they are called heat equation and called diffusion equation interchangeably. So this tells you that your rate of change of temperature in time is proportional to the second spatial derivative of the temperature. So the concavity of the temperature distribution tells you the change of temperature. So for instance, what if this was my initial state? So what if the pink line, is that visible? Sort of. What if the pink line, I should have done this at the beginning of class, sorry, Bill. What if the pink line represented your initial bit distribution? So here you've got, what's the sign? Is it positive or negative?
Negative.
And here you've got positive. So that tells us that as time moves forward, your differential equation is pulling this part in and pulling that part up. And so the diffusion or the dispersion here is trying to pull you toward that steady state.
Is this like how heat would spread over like an arbitrary surface, or like, no?
For right now, we've kind of got the simpler model. For a higher surface, we need more variables, and you can notice other behaviors.
So that alone shows exposure.
So I don't know that alone shows it's linear, but linearity is easy to check. But it brings me to my next point, so let me tell you what does it mean for an equation to be linear. Generally speaking, here's the form of a PDE. So the general form of a second order two variable PDE has to look like this. It's simply a function of all those variables. And yeah, we do like to treat each one as an individual variable. You can, if you want a PDE with more variables, then include more variables here. If you want a higher order PDE, then include more partial derivatives here. You see I've included at most two. And I guess I should put that t, second portion with respect to t in there also.
And you use the t is the same as the u of x.
That's correct.
That correct?
It's correct as long as they're continuous, which we're not going to belabor that assumption too much in this course. And so this is linear. The equation is linear if f is a linear function of u. If f is linear in u, the equation is linear. Let me give you a class exercise.
Ooh, fun.
Ken, which equation is linear?
So this is what I'm referring to when I say the equation. But in practice, it'll look like, one of the things that are on the board.
Wait, and you're saying like in U has an in between like the 0 to 100 boundaries, or linear?
Say again?
Like, what do you mean by in U? Like,
Oh, in this variable.
okay,
So considering it as a function of u only,
Okay.
is it linear in that?
it's a variable and a function, but, well, not.
U is a function, and capital F is a function of u and other. So actually, consider this equation. What is F? And second is this equation. linear. And I'll give you a moment to work that out before saying the solution. I haven't given you a chance to think. Does anybody want to volunteer an answer?
F is U sub t minus a u sub x equals 0.
That's basically what I heard. Yeah. And I've suppressed all the other variables just for expediency. So the equation is now f equals 0. And let us check if this is linear. So the way that you would check that is you plug in a linear combination of constant times u plus v. And you just see whether this is equal to f of u plus c times f of v, just by plugging in. And you can see that just by linearity of the derivative, this will be a linear function. I'll let you check the details, but you just take the derivative with respect to x and use linearity, and then take the derivative with respect to x again, and use linearity again. And then it breaks out as you like. We will learn how to solve that equation with lots of different kinds of boundary conditions, but I'll leave that for the rest of the course. For now, let me introduce the next two equations. There's three fundamental types. There's the heat or the diffusion equation. There is the wave equation, and then there's so-called Laplace's equation. So I'll show you those basic models now. So as you're going to kind of expect, wave equation describes the motion of a wave or vibrating string that's traveling at speed c. And so here's a model. You might consider like a guitar string or a plucked string in the following initial state. Right? You can imagine lifting the string up with your finger and then just letting it go. And uxt would then describe the displacement of the string at a particular time t. And Laplace's equation, why do we care about that? You also use delta U to denote Laplace's equation. If you look at the corresponding heat equations, so consider now the heat equation in two spatial variables. All of these you can generalize to multiple spatial variables. This one you just add, UZZ, UWW, so on and so forth. This one generalizes as follows. Or the diffusion equation generalizes like this, and wave equation generalizes to UTT minus C squared times Laplacian of U. So if you look at this heat equation, then I believe that Laplacian U equals 0. Describes the steady state. And maybe I can prove that to you later on in the course, but if you go back to that, and if you just believe me that I said this, which you don't have to, but we can return to it. If you then try to find the steady state by solving that equation, and since it's steady state, you might call it G, then you know that V is going to be equal to AX plus B, where A and B are going to be determined by your initial conditions. So in other words, yeah, it's a line. And so I need to fill in some details to sort of show that to you, but that's kind of where the theory is heading. So at least in just one spatial dimension, the story of what makes heat equation or diffusion interesting is not the steady state, which is just a line, but it's sort of how you're getting it, how you're diffusing the time. And I'll give you an exercise for Wednesday. So try and do this on your own, and we'll start with it on Wednesday. So I'm going to take something and ask you to show that it's a solution to the wave equation. So there's a procedure you can do to solve these equations, and we'll get to that. But for right now, I want you to actually verify that this actually solves the equation. In other words, this is a function of x and t. Take two t derivatives, and that should be equal to minus c squared times 2x derivatives. In order to do this, you're going to have to remember from fundamental theorem of calculus how to take the derivative of something with bounds. And if you want to simplify that, you could do something like this is equal to integration from 0 to x plus ct. plus integration from, x minus ct to 0. You know how you can split it up? And then you can look up the formula for how to take the derivative when you've got a function. There, you just use the chain rule. Yeah, so go ahead and try that out and bring it to class Wednesday, and we'll continue from there. We'll also put on some more information in the Google Classroom. So thank you, everybody, for your time and attention, and we'll see you on Wednesday.